Hey guys, welcome back. So now we'll be starting with the second part of the second chapter. It's a relatively small part compared to the first electrostatic potential which we were talking about. So now it's capacitance. And what is capacitance? So in this video we'll be covering two topics. The first one is all about capacitance and capacitors, their general properties, their circuit diagram notations and all. And the second part is the derivation for one of the most commonly used types of capacitors, which is called the parallel plate capacitor. So if you directly want to skip to the derivation, you can use the time over here. So yeah, let's start with capacitance. So what is capacitance? It is the ability of a body to store charge. It's as simple as that. So but the most efficiently, the electronic device which can perform capacitance in the most efficient way is the capacitor. So now let's see what's the general way of defining capacitance. Let's consider a capacitor is always made up of two bodies which are kept at a distance apart, and then the more complex ones, there can be many types of many bodies, or there are even cases where there's only one body. But generally and most commonly, it's just two individual bodies with charges opposite to each other. So let's consider two bodies over here. It can be of any shape: circles, plates, rectangles. So I'm just considering circles. So let's consider this is at a charge plus Q and this is at a charge negative Q. It has a potential difference V1 and this has a potential V2. This is free vacuum. It's just free space. You're placing it in space. Now let's whichever has a higher potential. Let's consider V1 has a higher potential. That is V1 is greater than V2. This is the condition we are taking. That means the charges would flow from V1 to V2. It always flows from higher potential to lower potential. So now the capacitance of this system, capacitance is the ability to store charges. So how strongly it can store charges. The capacitance of this system is given by the charge possessed by any one of the bodies, not both, any one, the magnitude only, so Q, by the potential difference between the two systems. Here potential difference is V1 minus V2 equals V, the potential difference, Q by V. And this is the capacitance of a given capacitor. We can modify this in a lot of ways. Each case there's a different modification. But generally, to proceed with the derivation, this is the base formula. This is what you need to be knowing to proceed with the next topic. So first we'll just, so we saw what was capacitance. So capacitor is the electronic device which performs capacitance. It is denoted by this symbol in circuit diagrams. It looks like a cell, but it is not. Both have the equal lengths. In a cell it's one shorter line and the other one is a larger line. So this is a capacitor, and if you need to show a variable capacitor, it would be in this way. Okay, so these are the basic things you need to know. Now let's proceed to the derivation. So this is for a parallel plate capacitor. Okay, so a parallel plate capacitor is the most commonly used capacitor for study purposes. It's the easiest to understand. So let's first draw the diagram. As the name suggests, it's parallel plates. It's two plates which are parallel to each other. And this ends are connected to a battery in a circuit. So how a capacitor functions is that the battery first charges the capacitor until they both become equal in potential. After that, there's no flow of current in the circuit. Now, if you remove the battery and if you now place a bulb or any other electronic device, this would now lighten up. That is, the capacitor which stored charges now discharges them and acts as a battery itself. So let's see how does it store the charge. We have the battery cell over here. The positive terminal accumulates positive charges on the left side of the capacitor and negative charges on the right side of the parallel plate capacitor. Let's call this Q, charge accumulated, and this is minus Q. So how do we proceed with the derivation? We know only one formula till now, and that is capacitance equals Q by V. This is the only thing we know. We don't know any other formula relating to capacitance. So obviously we have to do something to this. We can't change charge. Charge is a fixed quantity. Charge is fixed according to the battery's ability to share the potential. So charge is fixed. So the only thing we can change is potential. So let's see how to change potential. So first what we are going to be doing is find the electric field between the two plates. After we find the electric field over here, we can convert it to potential by using the formula we have already seen. V is equal to ER. This is the relationship between potential and the electric field at that given point. So then we find the potential and substitute it over here. So let's do it step by step. First step, calculate electric field between the two plates. Second step, convert it to the potential. Third step, substitute. So let's see the step 1. Step 1, finding electric field E. Now, if you remember, we have done this in the questions video of the first chapter. To find electric field due to two parallel plates at a point to the left, at a point to the right, and at a point at the center. We know at the left and right it's 0, and at the center there is a magnitude of sigma by epsilon naught. If you know the formula directly, you can skip to the time, or else I would show very quickly on how to find the electric field at these 3 points and show that it's 0 and 0 over here. So let's consider a point over here, P. So the electric field, the total electric field at that given point, E of P, equals the sum of the individual electric fields due to minus and positive charged plates. So let's first consider this plate. It's going to give minus sigma by 2 epsilon naught, and this is the formula for electric field due to a plane sheet. We have done this in the first chapter, which is sigma by epsilon naught is the sigma by 2 epsilon naught is the formula for electric field due to a plane sheet. But here it's minus sigma because the charge stored is negative. So the charge density is also going to be negative. Minus, minus. Now the positive's contribution is going to be plus sigma by 2 epsilon naught equals 0. So the reason it's becoming equal to 0 over here is because of the distance independent nature of the electric field due to a plane sheet. That means whether it's a point over here or a point over here or a point over here, the electric field is going to have the same magnitude, except the symbols will be positive or negative compared to which sheet you're using. But it's going to have the same magnitude at any of these points, which is equal to sigma by 2 epsilon naught. So we proved at the right it's equal to 0, and the same logic comes to the left and it's equal to 0. So now let's find it for the center. So now let's consider the same point P, which is at the center. Now the electric field over here is again going to be the individual contributions, but now let's see the directions. If we find the direction, we can add them up easily. So the positive is going to repel. P is always a unit positive charge. So the electric field at point P is going to be away, and electric field due to point minus Q, the plate minus Q, is again going to be towards it, but this time it adds up to the same direction. It's not in the opposite directions. When we consider over here, the negative attracts whereas the positive repels. When we consider over here, positive repels and negative attracts. Opposite directions, so they cancel off. But in this case, both the electric field vectors are in the same direction. Positive repels, negative attracts, same direction. So you just add them up with their magnitude and ignore their symbol. So it's going to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So the electric field in between the parallel plates is equal to sigma by epsilon naught. When you add them both, 2 and 2 in the numerator and denominator cancels off. So this is the electric field. So step 1 is completed. Now we have to proceed with step 2, which is find the potential. So I'll erase this off. So step 2 is convert to potential difference V. We know V is equal to ER. Now here we need to assume two quantities, which is a fixed quantity for a given capacitor, that the area of the plates equals A. The area of the plate is A, And now also another thing to assume is that the distance between the two plates is any, we'll take it as small d. So these two quantities are almost used in every numerical related to capacitors. So it's almost a part of the question. So here instead of R, it's going to be T. So it's going to be E times D. So the potential equals, we found E, which was sigma by epsilon naught. So it's going to be sigma D divided by epsilon naught. We are done. We can directly substitute it even now. But we are going to make one more modification for making it simpler for us. What we are going to do is, we are going to convert surface charge density sigma in terms of the total charge Q, so that you can cancel off this Q and this Q. So what is sigma? It's the total charge divided by the total area, and that's why we need A. So it's going to be Q by A times D by epsilon naught. So this is the total potential. So total potential equals Q by A times D divided by epsilon naught. Now you can notice one more detail over here, that it's epsilon naught. Epsilon naught, that means the space between the two plates is free space, it's vacuum. If there was a different material, which we'll learn in the next video, that is by bringing in a dielectric in between the plates, then it won't remain as epsilon naught and there will be one more small change. So now we are ready to substitute potential in the final answer. So I'll erase this off and we'll go to step 3. Substitute. So now capacitance equals Q divided by V, which we already found, equals Q by A into D by epsilon naught. Cancel off Q, and this is why we changed sigma. So we are left with numerator reciprocal. I'll write it in the proper way, that is epsilon naught A by D. This is the capacitance of a parallel plate capacitor. This is the final answer. So when we bring in a dielectric, like for example if you're bringing in a slab of thickness T, if you're bringing in the slab of thickness T, this answer would change. It wouldn't remain the same, and we are going to see this in the next video. So this is the end of the derivation. This is step 3. Okay, so in the next video we'll see how the answer would change if we are bringing in a dielectric of any length, any thickness T, or even any area. It could also be a shorter dielectric in this way, and then this has an area of say A dash. What would happen after that? So these cases we'll consider in the next video. So this is it for this video, and I'll see you all in the next video. Thank you.